Sophie
Okay.
give another lecture on KK theory. So I hope everyone is ready. Won't be quite the 4-hour last week. I'm sure it will be interesting nevertheless.
Yeah, thanks. Okay, yeah, so I will actually in the last part of this talk, I will continue where we left this last week Friday on KK-equivalence, and then I will also give you some more details about this split exact sequence, how to construct this explicit KK-equivalence, which I was talking about in my talk Tuesday. But first, I will explain for you another picture of KK theory by Cuntz. So both his quasi-homomorphism picture, and then another picture where he looked at some homomorphism between a specific ideal in a sister algebra, but I will come back to that. And then we will look at Higson's approach, which uses category theory. Yeah. So let's first start with the Cuntz quasi-homomorphism picture. So let me give you some motivation for it first. So if we just start with this. If we start with a Kasparov module, let's say a Kasparov AB module. So then remember that psi here will be a map from A to the adjoinable operators on E, and E is a B module. And then we have F, this operator inside L of E. I think last time we also was written with a B here to indicate the module. I think I will forget the B many times, but I think it should be clear what we are looking at. Okay, so now the idea is to put all information about this module into this map. So first we can assume that F is self-adjoint, and it also equals inverse. We can also assume that the norm is less than or equal to 1. So this follows by some standard simplifications, which we can always do, by finding some other Kasparov module which will be homotopic to the one we start with. So if you want a reference here, I'm not going to the details, but if you look at the book by Blackadder, then in section 7.4, these standard simplifications there are described. But now I will just assume that the operator satisfies this. So you are finding some other Kasparov module, and then maybe, so let me think, such that if you add it, so if you have some degenerated Kasparov module, then you can add it, and then you get still the same Kasparov module. But there's also something when you want to pass from here to here, then you define another operator, but then you get that they are operator homotopic still. Yeah. Okay. So I don't remember the details, but you can use some. It's not that difficult to use these standard simplifications, and then you can make this assumption. Okay. Yeah. So now let me first, if we look at the class here, we have ESI. Yep. Then the first thing I want to do is to add the Kasparov module E. 0 F minus F. So this is of course degenerated, because we have these assumptions on f, and we have just a 0. And if we add this, we get, oh, sorry, I want here e up, so e with the upper side grading. Then we get e plus psi plus 0, f plus minus. Okay. Because now I can use some unitary equivalence to change this operator here to a simple one. So if we look at the unitary u given by 1 over the square root of 2, then we have 1 minus f star 1. Then we get that this f 0, 0 minus f is the same as u star 0, 1, 1, 0 u. So it means that this Kasparov module we have over here is e plus e up psi plus 0. Is the same as the module e plus e up, and then we have to take u psi plus 0 u star, and here we, of course, we have the same here, that if we just take u on here and u star here, then we get this part here. So here we would have 0, 1, 1, 0. So if we use unitary equivalence, then we obtain that these two modules, they are homotropic. So I think that maybe you defined it in a different way last time. So maybe I should, I don't know if is it clear, or should I give the definition I usually, I don't know, did you explain unitary equivalence last? Yes, you also did that. Okay. Okay. But we get homotopic Kasparov modules if up to this unitary equivalence. Okay, so now you see, now we have changed our operator just to being this operator here. And then we can just, we know that we can express all modules of this form here. Some psi prime 0, 1, 0. So this psi prime here is just an instead of writing the same, but for some star homomorphism psi prime. Okay. So the next thing we want to do is to put all the information on the star homomorphism. So first, let me just recall, we had this last time, it was also defined this HB of all infinite sequences. Psi I with psi I and B, such that if we take the sum over psi I star psi I, then it converges. And then we have a natural grading on HB by letting all the degree 0 element corresponds to a sequence where all the elements in B comes from the degree 0 part of B, and the same with the degree 1 part. Okay. So now we know from also last time we saw the stabilization theorem. So now we have that E plus psi prime can be written as this HB plus HB up is a star homomorphism phi, and then we have this operator as before, which follows just by adding the module HB plus HB up is 0, and then with this same operator. Then we get by the stabilization theorem that these two Kasparov module they are homotopy. Okay, so this phi here is now a star homomorphism from A to L of HB. That's HB up. Okay. So now I want to look at what happens if B is trivially graded first, and then if both B and A are trivially graded. So if we have that B is trivially graded, then we also have that HB will just be trivially graded. And then we have, so HB is also trivially graded, which means that we obtain the standard even grading on LHB. HB, which is the same as the 2 times 2 matrices over L of HB. So it means that the degree 0 elements, they just correspond to diagonal matrices, and the degree 1 elements correspond to the ones having 0 diagonal. Okay. Because then we can write phi as a matrix here with some star homomorphism. So phi 0, 0, phi 0, 1, phi 1, 0, and phi 1, 1. Yeah. And then we want to look at this commutator here, the graded commutator. So we have that phi of A is 0, 1, 1, 0. That's the same as phi of A, 0, 1, 1, 0. And then we have minus 1 to the degree of phi of A, and then the degree of this operator here, which is just 1. And so phi of A. Okay. So it means that if A is inside the degree 0 part, then we just get that phi 0, 0 of A minus phi 1, 1 of A should be in K of HB by the condition of the Kasparov module. But when we have an A inside A1, then we get a plus instead of, and then we would have these two star homomorphisms. So we have phi 0, 1 of A plus phi 1, 0 of A being in K of HB. Yeah. So in Cuntz's picture, he assumed that both A and B, they are trivially graded. So if we also assume A to be trivially graded, then I let phi plus be phi 0, 0, phi minus just be phi 1, 1. And then we get precisely the condition which I also, the way I also wrote in my talk last time. how to express these Casparo modules. So then we get, of course, that phi plus, phi minus. They are maps from A to L of HP, which we can also see as the multiplier of K tensor B. And we have that phi plus of A minus phi minus of A has to be in K of HB, which is the same as isomorphic to K tensor B for all A in A. Yeah. So now, using this argument here, it is possible to express each Casparo module by two maps such that this condition here is satisfied. So we have put all information in the star homomorphism, and we don't have to consider the module or the operator anymore. So now what Cuntz did was to give a more general definition of what these maps also falls into with this condition. So here he looked at these quasi-homomorphism and quasi-homomorphisms. Maybe I should also say here that the degenerated elements will be precisely the one where you have phi plus and phi minus are the same. Yeah. Okay, so let me give you these definitions, and then I will give you an overview over what Cuntz actually did. So a après quasi homomorphism from A to B so it consists of a sister algebra, which I will denote by E. So not to be confused with the E and the Casparo module, but we have a sister algebra E. Then we have two star homomorphisms. Alpha and alpha bar from A to E. And we have an ideal inside E. An ideal J inside E. And also a star homomorphism mu from J to B. So here we also get how J is related to B. There should be a star homomorphism here. Such that if we take alpha of A, so yeah, we call it X now, minus alpha bar of X, then it has to be inside J for all X and A. Yeah. So you see that this here will be an example of a quasi-homomorphism. Then you need mu to be just the identity map in this case. And we use the notation like this. So we have A, alpha bar, the two maps to E. And then we have our ideal J. And then the map mu to B. Yeah, so let me give you the examples. Okay, I don't have space here. I will erase it. Then let me give you the examples. So if we take these maps we looked at before, then we have, if we have our A, then we have the two maps 5 plus and 5 minus to M of K tends to B. And then we have that our ideal is just K. So in this case, J and B, okay, the B in the definition over there is just the same. So we don't have, we have the identity map here to K tends to B. What do you say? Yeah, so the B I have written over here is just K tensor. And yeah, the notation maybe it's, yeah, but that, yeah, I have used the same notation as he do in his paper. So yeah, so in this case here, we just have mu as the identity. A more easy example is, of course, if you have just a star homomorphism from A to B to sister algebras, then we have that A taking one of these star homomorphisms to be alpha and the other one to be 0. And then just taking the ideal to be B itself. And then, of course, again, mu to be the identity map, then this is also a pre-quasi homomorphism. Yeah, okay, I wrote J and E, it can also be equal to E, yeah. Why I did that? No, it was just to, when I have to consider them later on, I wrote them like that. It's not. Mm? Yeah. Yeah, so we just have these two maps. So phi 0, 0 and phi 1, 1. So we only have the maps on the diagonal because when A is trivially graded, these maps are just 0.
That's the degree 1 part.
Yeah, exactly. The degree 1 part. Yeah. So first, assuming B is trivially graded, we can write it like this. And then when A is also trivially graded, we only have the degree 0 part of it. So these two are just 0 here. Yes, so this is just phi plus and this is phi minus. Yeah. You can also call them phi 0, 0 and phi 1, 1. Yeah, so Cuntz picture works for trivially graded sister algebras. But we can also, if you have two sister algebras, you can always make them trivially graded. Yeah. So it's only possible here to put all the information into these, since I have assumed that they are trivially graded in the end. Yeah. Okay. Okay, so then he also defines what quasi-homomorphisms are, and they are a special case of quasi-homomorphism. So a quasi-homomorphism is a quasi-homomorphism for which, yeah, I will give you the definition. It's not that I will use these conditions later on because I will not provide you with any technical details or proofs. But let me give you the definition still. So we have first that mu should be an inclusion. Then we have that E, the sister algebra E, is generated by alpha of A and alpha bar of A. So if you take the image of these two maps, alpha and alpha bar, from A to E, then you get all of E. If you take the sister algebra generated by these two here. And then there are two more conditions. So J, this ideal J, is the closed two-sided ideal inside E, generated by alpha of x minus alpha bar of x for all x and A. So we know that this is assumed to be inside J, but it should actually be generated by these elements. And then there's the last condition. So here Cuntz actually uses two different definitions for the last part, but says that it gives the same results in the end. So if we take pi to be the map from E to E quotient with J, then then pi composed with alpha is injective. And in his first paper, where he considered these quasi-homomorphisms, he defined these quasi-homomorphisms by the first three conditions, and then in the end, here he says that J should be essential instead of the last condition here. Yeah. What do you say?
It's equivalent.
Yeah, these two different. So in the end, when you want to look at, when you want to construct, describe KK theory by these quasi-homomorphism, then you get still KK theory in the end. So it doesn't matter if you use this or the other one. Yeah. Yeah. Yeah, you could take J to be B. Yes. So if we have, like our example here, so the motivation I started with, sorry, this one here we have that the ideal J is just B. So it's actually, I will come to it, but you can always construct a unique. I will specify what I mean by unique, but a unique quasi-homomorphism from each pre-quasi-homomorphism, so they are related. But I think it will become clear why we both use the definition of these pre-quasi-homomorphism and the quasi-homomorphism later. Yeah. Yeah, but then it's possible to construct from each of these quasi-homomorphisms. It's possible to construct a Kasparov module from each of them. So if we have a quasi-homomorphism, alpha bar E J inside K tensor B. So a quasi-homomorphism from E to B. Then it gives you a Kasparov module by taking pi to be alpha 0, 0, alpha bar, and f to be 0, 1, 1, 0. So just as we saw in the first motivation I gave you. So there are some technicalities when you want to have these, you have to extend some of the maps and embed K tensor B into matrices over K tensor B. So there are some technicalities. I will not go into that, but if you want to look at them, then you can look at Cuntz paper from 81, section. So here it gives the technicalities to construct this Casparo module from a quasi-homomorphism.
J and K that means two inclusions. J and B and
So you're saying J in?
sorry. So you
Yeah.
have U is an inclusion.
Yeah, mu is an inclusion.
J is B.
Yeah.
And then B sits in K times B.
Yeah.
So it's a composition of two inclusions.
Yeah. Okay. Yeah. Like that. Okay. So now let me describe for you why this why we want to look at these pre-quasi homomorphisms, what makes KK theory easier when we use this picture instead of Casparo modules. So here I have been looking at Cuntz, two papers by Cuntz. So the first one from Etsy1. Here he defined KK of AB as homotopy classes of these quasi-homomorphisms from A to K tensor B. I will not use it. I will not use it anymore. This picture here, but there's a way to define homotopy equivalence of these quasi-homomorphisms. So maybe if we have time in the end, I can give you that. But the point is that then he proved that two homotopic quasi-homomorphisms isn't one-to-one corresponding with that the corresponding Casparo modules are homotopic. Okay, but the important thing with this picture is that it makes the Casparo project easier to compute, or at least it's easier to prove that it exists and it is associative, which is what he also did in this paper here. So so as you see here, we avoid all these technicalities using graded algebras and Hilbert modules, also the stabilization theorem. So we have removed a lot of things which we actually saw last time, and instead we just look at these homotopy classes of quasi-homomorphisms. What does it? Yeah. So where? In this picture, okay, yeah, exactly. So here let me say that here the product, because of course there are some technicalities. Yeah. So here you have that the product corresponds. So if you have two of these beta bar, and then taking the product, then we get some alpha beta, beta alpha, and then a certain beta alpha bar. Okay, so it's not clear how to compose these two, of course, directly. So you need to do something such that you can extend these maps and then compose them. So he talks about these composability of these maps. So of course, so it's easier to prove the existence of it. And then so for these split exact sequences I have been looking at, where here I've used actually this picture here. So here it is easier to compute the product, at least for these split exact sequences, because we use split exactness of KK theory. But otherwise, when I have been looking at calculations where you have using the Kasparov, the Kasparov project as you defined it last time, then there are of course some ways also to compute the product, but of course computing the product is difficult, and it's also difficult here, of course, but proving that it exists and it is associative is easier when you look at this picture. Yeah. But I don't have so much experience in actually computing the product. So yeah. Yeah. Gives a Kasparov module. Exactly. Yeah, exactly. So it's 1-to-1, and then he proved that this notion of homotopic quasi-homomorphism gives you precisely that the corresponding modules are also homotopic. Yeah, so what I started with was one direction. If you have a Kasparov module, we get quasi. What does it? What do you say?
It always has a trivial grade.
Yeah, everything here is trivially graded system algebras. When you look at this picture, yeah, exactly. Okay. But of course, I'm avoiding. Yeah, I'm not giving you many technicalities because it, of course, takes a lot of time. But the main idea is that proving existence and proving its associativity becomes much more clear, and you avoid a lot of technicalities. Yeah. Okay. So now in his second paper, here the idea was to improve and extend this method. And now KK of AB is defined as homotopy classes of homomorphisms from a specific algebra called QA. I will define it for you soon, but this is a subalgebra of the free product, the system algebra, the free product of the system algebra A with itself. I will also explain for you what this is. So, okay, tensor B. So here it's actually an ideal in a free product of A with itself. So now you see that now in this picture here, homotopy is just homotopy of homomorphism between these two system algebras. And Cuntz also write in his introduction that, partly this is also motivated by the fact that he wants to maybe remove the system algebraic condition. So maybe looking at rings or something like that, because when you look at this picture here, it's not necessarily that they need to be system algebras. Yeah, but we will see that that we precisely get KK theory for system algebras. Here it is, of course, important that they are. He uses that they are system algebras. So this is just a motivation for research. Okay. Let's see what else. Yeah. So here I will just write these homotopy classes of this group here as QA. Yeah, and there's also a reason why we look at K tensor B and not B, and it's because that this here, it shows that this will only be a group if this is a stable system algebra. Yeah. Okay. What is that? It's just homotopy of these homomorphisms from these between these two system algebras. So should I recall it? What? Yeah, I will come back to how they are related to here, because actually so here he proves, of course, in the first paper that we get KK theory using these homotopy classes of quasi-homomorphism, but these maps from QA to K tensor B, they are related to these pre-quasi-homomorphisms. So you can describe all these maps here using pre-quasi-homomorphisms. But I will explain it. Yeah. I will come to it now. QA, yeah, it's an ideal in a system algebra. Yeah. No, but it's the next thing. Yeah. But just to give you an idea of what this paper is about. And again, now the product becomes actually even easier to prove that it exists in that picture, which I will also come back to. Okay, so let's look at the ideal QA. So I said this is an ideal in the free product of the system algebra A with itself. So let me first give you the definition of the free product. So a system algebra C is the free product of a system algebra A and B if there are some star homomorphisms. So one from, I call it IA, one from A to C and another one from B to C, which satisfies a universal properties. So if we have so satisfying the universal property, that if we have another system algebra D and we have some maps phi A from A to D and from B to D, some star homomorphism, then there exists a unique star homomorphism from C to D. Such that if you take phi and compose it with phi, compose it with IA, then you get phi A, and the same for B. Yeah. And then it can be shown that this free product always exists for these C-star algebras. This was also something new for me, and I looked at this construction, and it uses a lot of taking a lot of tensor product and a lot of other things. I cannot do it in a short way, but this free product, it exists always for two C-star algebras. So now we want to look at the free product of A with itself, and I denote it by QA. And then we have two canonical inclusions of A into QA, denoted by I and I bar. Okay, so now I can define this ideal QA. So QA is the ideal. And two-sided closed ideal. Inside big QA generated by this set here of I of X minus I bar of X, X and A. So I think so. This looks familiar. Oh, okay. So I'm actually not aware of that. So here what I did, I looked in this Jensen and Thompson book on KK theory, and here they defined this free product in the end of the book. And this, yeah. So I think we can figure out what it is. Yeah. No, yeah. Okay. 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 Yeah. Yeah. So as I said, this is also new for me. So yeah. Okay. No. So then, if we have two star homomorphism from A to E, as we know, we have when we have a quasi homomorphism, then we know that there exists a unique star homomorphism, which I denote by Q of alpha bar, from QA to E, just by the universal property. Okay, such that, yeah, Q of alpha bar goes with I gives us alpha, and Q of alpha bar goes with I bar gives us alpha. Okay. So now, if we have an ideal inside E, which is the case for these quasi homomorphism, ideal, then this Q of alpha bar maps our ideal QA into J, if and only if J satisfies the condition that alpha X of X minus alpha bar of X is inside J for all X and A. which is also what we have assumed for these pre-Cross-Isomorphisms. Okay. So now we can almost see the connection between these maps and these pre-Cross-Isomorphisms. Okay, so if we have this tuple J E mu, if this is a pre-Cross-Isomorphism, yeah, I didn't use that notation before, but we also use the notation with this tuple instead. If this is a pre-Cross-Isomorphism from A to B, then we obtain a star homomorphism when we take mu and compose it with this map Q alpha alpha bar and Q alpha alpha bar with the little q is just the big Q restricted to the ideal QA. So then we get this map here from QA. So now you see that every time we have a pre-Cross-Isomorphism, we will actually get a map from this ideal to B. Okay. Now it turns out that all maps from QA to B comes from a pre-Cross-Isomorphism. So it also goes in the other direction. So this is what Cuntz proved. So he proved that there is a bijection between the set of quasi-homomorphisms from A to B and the set of homomorphisms from QA to B. Exactly. Yeah. I will make a note about it now. So I was just thinking. So he gives an explicit way to see this bijection. I will not write it now, but we already saw that if we have a pre-Cross-Isomorphism, how we get this map, and then there's an explicit way to get the other way around. But but note that if we have a Cross-Isomorphism, A alpha alpha bar to E J B. So then we can associate a unique quasi-homomorphism. A, and then we have some alpha prime, alpha. We have some other cyst algebras here, E prime and J prime. But we still have our A and B, of course, such that this map Q of alpha prime, alpha bar prime is the same as if we would take mu and compose it with Q of alpha bar. So unique in that sense that that this is satisfied. Yeah, so that's why we jump a bit between these pre-quasi-homomorphisms and quasi-homomorphisms. Yeah. So do you normally have a break, or do we just? Okay. 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 Okay, so let me maybe summarize just a bit of this. So if we have, so we call this this quasi-homomorphism A. Okay. Okay. Yeah. Okay. So we have this this universal quasi-homomorphism. This one we started with here, where we have these canonical inclusions. So this is the universal homomorphism, because if we have another one here, alpha bar, with an ideal J, then we know we have this map, big Q of alpha bar, and then we obtain this map, Q of alpha bar. So when we have a quasi-homomorphism, we don't have this mu here because it's just inclusion. So we have this map here, and these are known as the classifiable so this diagram okay, so now Cuntz proved he proved that this group here of all homotopy classes of maps from QA to K tensor B, that this is an abelian group. And here it is important that this is stable. This is algebra here, but of course it is if it's with K. And the zero element is just corresponding to the zero. And then if we have two elements, inside tensor B, inside the group, then addition is defined by taking a map tensor B, which is the map from the 2 times 2 matrices over K tensor B. Because if we need a way to add these two, but if we take this map theta B on these matrices, and then we just put these two homomorphisms into a matrix like this, then we define this as the addition. Yeah. Okay. So now let me say a few words about the product, because in this case, in this picture here, again, the product, existence of the product and associativity becomes more clear. But of course, there's still some technicalities. So if we take an element inside KK of B, in this picture here, so a map between map from QA to K tensor B, and we take another one, B to C. So here we have a map from QA B to K tensor C. And now the question is how to compose these two maps, because then we would have a product. So first, so the first thing we can do over here is to take Q, both sides. This is a functor Q, so we can do this. And over here, we take K tensor QB, and of course, if we tensor K here, we still get K tensor C. Yeah, and then there will exist a map here. By universality. So now we have a map from Q, taking Q twice, and A, so K tensor C. So now the technical part lies in showing that that we get a map from QA to K tensor C. And here, what Cuntz showed is that if you take the class of the multiple class of maps from Q to the square here, A, to K tensor C, it is the same as taking the class of QA, K tensor C. And this part here requires some work. Yeah. But as you see, the rest of it, getting a map from here to here, will follow by the universality condition. And then it boils down to proving that this is true. Yeah. And then he also proves, of course, that defining the product in this way gives us a bilinear and associative product. Yeah. So just to summarize, so the first picture was to look at these quasi-homomorphisms, which are in one-to-one correspondence with Kasparov modules. And then the second one here was to look at these maps between QA and K tensor B, which is then in one-to-one corresponding with pre-quasi-homomorphisms. Yeah, and then it all describes KK theory in the case where we have trivially graded system. Yeah. Oh, sorry. Yeah, of course. Okay. Yeah. So to have the product, we still need the same condition as we usually have. Yeah, exactly. Yeah, that's of course important. Yeah. And he also, in his paper, he also looked at a product when you have not just KK0, but also KKN. Okay. So I think I will move on to say a bit about Higson's approach. Which uses category theory, and it relies on Cuntz approach, quasi-homomorphism picture. So what Cuntz did was to look at a category, K, no, to note it like this, for which we have that the objects separable cis-algebras, and the morphisms from A to B is the KK group of A and B. So first, see immediately if we let C star note like this, be the category of cis-algebras. Again, separable cis-algebras. And just usually star homomorphisms. Then we get a canonical functor. C from this one, from this category here. So K, the other category K. Just by taking C of a star homomorphism from A to B and mapping it to the class BF, zero. If F is a map from A to B. Then we get a class in KK of AB. So now the idea is to show that what he did was to show that this functor is a universal functor satisfying three conditions into the universal functor into an additive category satisfying some conditions. So first, we have, of course, that K, this category K here. It has a law of composition. Using the Kasparov product. So if we have X and KK AB, and we have Y and KK BD, then we can compose Y and X by taking the product. And now, since the product is associative, so we know that the product is associative, it's bilinear, plus we know that KK of AB is abelian. Then we obtain that K is an additive category. Okay, so now let's look at a functor f from this category here into just an arbitrary additive category. If we take an object x in A, we fix such an object, then we obtain a functor, so a covariant functor, denoted A, X, and we have F, going, taking just a sister algebra. It goes from the category of sister algebras with star homomorphism into abelian groups. So we take a sister algebra, and then we look at all the morphisms from X to f of B. Okay. And now we want this this functor here to satisfy some condition, which will turn out to be the condition we need for this C to be a universal functor. Yeah, but first note that so the first condition is that we want A to be a homotopy functor. Second, we want it to be stable. Meaning that if we have a separable sister algebra B, the map A of X f of B to A of X f of K tensor B. This is an isomorphism. And this map is obtained by the map from B to the compact operator tensor B, where you map an element in B to B tensor, rank 1 operator in the compact operators tensor B, just as we saw last time also. Yeah. And then the last condition. Sorry, what did you say? It's opposite. I don't think so, but I'm not. Okay. Yeah, yeah. Um,
So how does the additive structure on A or this sample category come to play? Because the category is because it's not itself, right?
So it is that if it will be the universal functor from this just a category of sister algebras and star homomorphisms into additive category, but not
Yeah, so that somewhere technical details related to this requirement, because from the point of view of the category, there is no such thing as the sum of two numbers. So yet somehow, but it is maybe some library.
yeah. I'm not sure about these techniques. Yeah.
I mean, usually when you're using these algebras in sort of functorial ways, you always want to do things like stabilize. So in that case, you could have homomorphism in a direct sum kind of way. And get a homomorphism, like down the diagonal matrix.
Okay. Yeah. So the last condition is split exactness. So it should be split exact functor. Yeah. So if we have a sequence, split exact sequence of sister algebras, split exact, then we also get a split exact sequence like this. J. Oh, sorry. This should be. And then there should be a split exact. So note that if in the case of this category K, we have that K some X. This is precisely just taking the KK of X, taking the KK groups. And here we saw last time that this functor here satisfies all these conditions. Yeah. Okay. Now I can state what Higson proved. So if we'll just let F be functor between these two categories, and again we have this is an additive just the setting as before, an additive category, such that for each object X in A, we have that A of X so we have that this satisfies precisely condition 1 to 3. So then there exists a unique functor from this category K to A. Yeah, such that if we compose it, C, we get sorry. The functor has to be additive. Yeah, if this has to be. Yeah, it goes from the additive category to another. I'm actually not sure about that. In his paper, he just wrote that there should exist this unique functor. But I'm actually not sure if it's additive or, but it makes sense that it should preserve the additive structure. Yeah. Sorry? Yeah, exactly. Yeah. Yeah. Okay. Yeah, but this is actually what I wanted to present about Hickson's approach. So he also have another main result saying that that if you have a functor on the category of sister algebras, several sister algebras, and it's stable and split exact, then it's automatically homotopy invariant. Which is also what I would like to mention it because it's also one of the main results in his paper. So you get homotopy invariant from the other two conditions. Yeah. I don't know if there's other questions. Otherwise, I will. Yeah. Yeah.
Does the functor C that we define using full picture? From the star form from A to B, you create the star form from UA to B. Okay.
So one more time. So you'd say if you take
instead of sending F to
here
class
of this one,
F to,
but then you just have this class of if and the zero map in the Cuntz picture.
and
Makes sense. So if you have okay. So if you have, I gave this the first example that if you just have a star homomorphism, then you can produce a quasi homomorphism just by letting one of the maps be zero and the other one be F. Yeah, exactly. And then this mu would just be then the ideal would just be the sister algebra itself, and the inclusion. So you just have the ideal is the same as the sister algebra, and then the inclusion is just identity. Exactly. Yeah. Okay.
sorry, so to make sure about this, you said homotopy follows from stability and splitting up.
Yeah. And so I can give you the reference because this is in his paper from 8080. So algebraic K-theory of stable sister algebras. Here, this is a main result in that paper. Therefore, I would like to mention it. Yeah. Yeah,
amazing.
exactly. Yeah, exactly. So he proves that if you have this function on this category of several sister algebra and it's stable and split exact, it's automatically homotopy invariant. Yeah. No, just one from these separable sister algebras. The categories.
And the category A is just anything active.
Yeah, like in this case. Yeah. Yeah. Okay, I'm not sure about that part. Yeah. Yeah, I can look it up. Yeah, yeah. Because then let me say a few words about KK-equivalence. Let's see. Okay, so let me give you just a definition again. So if we have to separate and we have an element x inside KK of AB and another one inside KK of BA. Such that if we take X product with Y, we get the identity on KK on AA. And if we take the other one, get the identity then we say that A and B are KK. Yeah, and we write it as AK. Okay, so as it was also explained last week, that if we have that they are KK equivalent, we get that all the KK groups, they are isomorphic, and we have an explicit isomorphism just by using this X and this Y. So I will not write it again. And instead I will look at some examples, and in particular this split excitements. Yeah, and again, some of these examples we also saw them last week, but we always have that A is KK equivalent to the matrices over A, and we also have that it's KK equivalent to K tensor A. Then we also saw that last time that the complex numbers is KK equivalent to C0 functions on R, which follows by Butt periodicity. And in more general results, we have that A is KK equivalent to taking the suspension twice, which was also mentioned last week. Then let me also mention again this UCT class. I will not go into the details, but as I also mentioned in my talk, that if we have these sister algebra satisfying what is called the universal coefficient theorem, then the KK theory is completely given by the K theory. So just have to look at the K-tree to determine if they are KK-equivalent. And one thing else I also want to mention is that if we have a separable sister algebra, if we say that A is a separable sister algebra in the UCT class, then it is KK-equivalent to a commutative sister algebra. But as you saw in my talk, knowing that it is in the UCT class was very useful to concluding if these sister algebras was actually KK equivalent, because, for example, we know that all the commutative sister algebras, they are in the UCT class. We also have the compact operators, and then the fact that they were closed under taking extensions. Yeah. So now, as the last thing, let's look at these split exact sequences again. Yeah, so I'm sorry, I'm repeating myself, but I planned this to have been a talk given before my talk in the beginning of the week. So yeah, but let's look at this split exactness and KK theory. So as I mentioned in my talk, if we have a split exact sequence, so splitting we denote it by S, quotient Q, and then we have a map G. So if this is a split exact sequence, then E is KK equivalent to J plus B. Using following class, so we take J plus S, which gives us a class in KK of J plus B. Yeah, so I can then give you an explicit inverse to this class here. So let's do that. Okay, so we need an inverse alpha being in KK of E J plus B. Okay, and it's given by Okay. Ah, okay. The light. Yeah.
That's supposed to here. Then this is a concept. I think that's it. Okay. If you want to look at it in the terms of graded Casparo modules, then it corresponds to taking J, taking opposite one, and having this canonical map from E to M of J to the multiplier of J, which comes from the fact that J is an ideal of E. This plus W equals S equals Q. And then it will always also get an element in KK of D. So here we have the Cuntz picture, and here we have this picture using the Casparo object. I think that's okay, but I would just want to say why we use this quasi homomorphism picture here. So it's actually because we found the proof much easier when we looked at it actually followed from the proof of split exactness of KK theory using the quasi homomorphism. Yeah. So maybe just as a final thing, let me give you some reference.
So E goes into K tensor E,
Yeah, K tensor E.
and then RJ domain.
J goes from a multiplier of K tensor E. So you have
Okay.
So and then of course it's continuous. So we
Yeah.
need to look at RJ on elements in K tensor E.
Right.
Okay. Some references. So for this Cuntz picture, we have this. I have these two papers. So we have just generalized. Sister atoms. It's one, and then we just saw that if we look at somewhere places also 83. Yeah, I'm not sure. Which one? And then we have, so this is on this quasi-homomorphism picture. And then we have the other one looking at these homotopy classes of these maps. This is a new look. And also, and then of course these are the same references as we had last time. This the book by Blackadder and elements of KK-equivalence by Mikkelsen and Thompson. Sensation. Yeah, I think that was the most important reference. Frequencies.
So this was an exercise in Blackadder's book, you said.
This is an exercise by
And this is the solution to the exercise.
the solution to the exercise. And then we, instead of using this picture here, we found more convenience to look at the quasi.
I see. So the way he phrases it is in terms of the
Yeah, because then he says that this should be the pi s you have to use.
right.
So he says which pi has to use, and then you have to show that this is a KK equivalence. Yeah, and here we found it the easiest compute when we look at the quasi-homomorphism pictures.
And I mean, in terms of doing the product to show that it is.
Yeah, so here, so to show it is actually follows from the proof, which shows that that KK theory is exact. Using the quasi-homomorphism picture. So yeah, so it follows from that proof. Yeah.
So on the Cuntz picture, you can't deal with grading. So what is the grading offer you in the non-Cuntz picture? Why grade things other than to make your life more difficult?
That's one question. They differ and the rest.
Hmm?
Differ and the rest. They have an inherent gradient.
Yeah.
Dot part of them that is there. Yeah.
But do you ever gain anything by not just considering the trivial grading? Do you get something different?
Taking the when you're taking the index of the direct operator, use the gradient because it should go from positive to negative. Otherwise, because these operators are subjoined, this is in the right then the index would be trivial. So this is at least coming off from the differential operator point of view. That's where the gradient is there.
And that should be trivial.
Yeah, if it's a self-adjoint operator, then the index is 0. The kernel is the whole kernel. But if you introduce the grading and you consider it as a map from the positive to the negative, then you get non-trivial grading. It's going to be like the Euler characteristic. That's why my understanding of the grading is there, but that doesn't answer your question.
I mean, like, is particular case in class always James one is non-grading?
Yeah.
Is that grading?
understanding.